Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Sakina and my matric number is 076952 076952. So today I will introduce to you guys my group project. So artificial intelligence AI is widely used to solve decision making and pathfinding problems. This project focuses on a smart parking allocation system that help drivers find parking spaces quickly and efficiently. The system guides a car from the starting point to the nearest available parking space while avoiding obstacles. Several AI search algorithms such as breadth first search, deep depth first search, greedy best first search, and A-star search are implemented and compared. This project helps analyze which algorithm provide better performance in terms of speed, pathfinding, and efficiency. So next is problem description. So finding an empty parking space is difficult in crowded area like shopping mall and universities. Drivers often waste time search randomly for parking spot, causing traffic congestion and fuel wastage. In this project, the parking area is designed as a grid where the car can only move up, down, left, and right. The car must find the nearest parking space while avoiding blocked area and obstacles. The main challenges is to determine the best path efficiently. Different search algorithms produce different results.
Assalamualaikum Doctor, my name is Zadi Arisha binti Bakri and my matric number is 077613. So I will explain about my part, which is the search problem formulation. So in this section, we model the parking lot as a 5x6 2D grid, which Doctor can see in the slide. Our agent, which represent the car, begins at the initial state of 00. The objective or goal state is to reach the available parking slot at 05. To move through the grid, we define a successor function that allows the car to move in 4 directions, which are up, down, left, and right. However, the agent must navigate around obstacles, which are represented by X. We assign a path cost of 1 for every movement, meaning the system is designed to find the solution with the lowest total cost or the fewest number of steps. So for the next part, I will explain about the algorithm implementation. In this part, we implemented the system using Python. We compared two categories of algorithm, which are uninformed and informed search. Okay, under uninformed search, we tested BFS, which is highly reliable for finding the shortest path, and DFS, which is memory efficient but often finds longer, non-optimal routes. To optimize the search, we introduce a heuristic called Manhattan distance. This helps the agent guess how far it is from the parking spot, while greedy best first search is very fast because it only focuses on the heuristic. The A search algorithm proved to be the most superior. This is because A balances the cost already traveled with the estimated distance remaining. It is both complete and optimal, ensuring the car finds the absolute best path while expanding the fewest number of nodes. That's all from me. Thank you.
For the smart parking system, we use something called Manhattan distance as the heuristic. It helps us to estimate how far the car is from a parking spot using only up, down, left, and right movements. We calculate it using the difference between the current position and the goal position in both row and column. In A-star search, we also use a total cost function, which is Gn plus Hn. Gn is the actual cost from the start and Hn is the estimate cost to the goal. We use this because it is simple, fast, and works well for grid-based system like parking. This heuristic is admissible, which means it never overestimates the real cost, so A-star can always find the best path. It is also consistent, meaning the cost increases smoothly between steps, so we do not need to revisit nodes. Without heuristic methods like BFS or DFS, the system will explore many unnecessary nodes and become slower. But with a star, the search focuses directly toward the goal, making it faster and more efficient. Now for the complexity, BFS and S-star have similar worst case time complexity, but BFS use more memory. DFS use less memory but does not guarantee the shortest path. Greedy is fast but not always correct. From our results, all algorithms can find a path, but S-star gives the best and shortest path. So overall, S-star is the most suitable algorithm for this smart parking system. Now, I will explain the smart parking allocation system using the S-star search algorithm. In this system, the grid represents a parking area where S is the starting position of the car, G represents available parking spots, X represents obstacle, and P represents parked car that cannot be passed through. The system used the A algorithm to find the best part from the car to the nearest parking spot. It works by combining two values, the actual cost from the start, called Gn, and the estimate cost to the goal using Manhattan distance, called n. Together, they form Fn equal to Gn plus n. The Manhattan distance is used because movement is only allowed in 4 directions, up, down, left, and right. This makes it suitable for grid-based navigation. The algorithm evaluates all possible parking goals and selects the one with the shortest path. This ensures the car reaches a parking spot efficiently while avoiding obstacles. Overall, S-star provides an optimal and efficient solution for smart parking navigation. Now, I will explain the smart parking allocation system using the S-star search algorithm. In this system, the grid represents a parking area where S is the starting position of the car, G represents.
For optimization techniques, this project used three main methods. First is visited set optimization, where exploit nodes are stored to avoid repeated searching and improve execution speed. Second is improved heuristic using Manhattan distance, which help the algorithm move toward the parking spot more efficiently. Lastly, state space reduction is used to ignore block cells and reduce unnecessary paths during the search process. This technique helps make the smart parking allocation system faster and more efficient. For the result comparison, all four algorithms were tested using the same parking grid environment for a fair comparison. The performance was evaluated based on node expanded, time taken, memory usage, and path optimality. BFS always found the shortest path by using high memory and expanded many nodes. DFS was faster and used less memory but did not always give the best part. Greedy best first search was the faster and expanded the least noded, but the path was not always optimal. Overall, A search gave the best performance because it balanced both speed and accuracy, making it the most suitable algorithm for the smart parking system. So, the conclusion of this project is successfully demonstrate the use of AI search algorithm in a smart parking allocation system. The system can guide to the nearest parking space efficiently while avoiding obstacles. The project compared BFS, DFS, Greedy, and AI algorithm. Among these, the most better one is A search because they use heuristic and path cost to guide the search process. Overall, this project improves understanding of AI search techniques and show how AI can help reduce parking search time and improve traffic flow in parking area. So that's all from us. Thank you.